Alright, this is a short video that is an introduction to the Laplace transform. So, the Laplace transform of a function, the input function if you want to call it that, the red f here, is itself a function. So it's going to be denoted by this fancy L, and you're plugging in this function f, and it spits out a new function whose independent variable is s. And what do? What does the Laplace transform do to a function? Well, it plugs it into this goofy integral. So it takes the integral of your red function, but it multiplies that red function first by e to the minus st. And also notice this is an improper integral from 0 to infinity. So an integral along the non-negative real axis. And so the Laplace transform exists whenever this integral converges. Remember, it's a type of limit. I'll say more about that a little bit later. So not every function has a Laplace transform, and for a differential equations class, you'll typically focus on the functions that do have Laplace transforms. When it's understood what little f is in red, on the left side over here, that's a whole lot of notation. So it's pretty common for books also to just use a capital F. And so capital F is the Laplace transform of little f, is how you should think of that. So same formula, just maybe a slightly easier notation. Now, what I was saying a minute ago, the types of functions that little f will be, that we'll take the Laplace transform of, in other words, they'll typically be polynomials, exponentials, trig functions, and hyperbolic trig functions too. Stepwise or piecewise functions, which I'll mention in a different video, and then any sum, product, or power of these. We'll look at how we can try to do those. So let's try to do one of these. Let's try and use that definition to compute the Laplace transform of this pretty nice exponential, just e to the t. So we've got to remember the definition here, which says you should just plug your red function into that formula on the integral on the right. So let's try and do that. So that looks like improper integral from 0 to infinity, e to the minus st times e to the t dt. Now, I can use some exponent rules to combine those exponents into a single exponential. And what else? T is the variable of integration, so I'll factor a t out of that exponent. So you'd have 1 minus s left over. Now what we'll do is we'll try to integrate. And so if we're thinking about what's a good antiderivative for this exponential here, remember antiderivatives and fundamental theorem of calculus make sense if this was like from 0 to 1 or from 0 to 2. How do we try to make sense of this from 0 to infinity? We think about this as a limit. It's going to be the limit as I take this right endpoint and let it go to infinity. But the point though is that if that's a fixed n for right now, maybe n is 1 say, well then it makes sense to apply the fundamental theorem of calculus and take that antiderivative, use my antiderivative rules. So remember, just 1 minus s just comes down underneath the reciprocal. That comes down is another way to say that. So I've got my antiderivative for this, and now I'm going to evaluate it with this limit. So I'll plug in the top endpoint. So n is t, so change this t to this n right here. And then take that limit, and then when you plug in t equals 0, you just get 1 in the top, and you still have 1 minus s in the bottom. So that's me finishing the fundamental theorem of calculus. Now let's take this limit here. Maybe notice too that, well, how do you compute the limit of this? Well, if this is negative, then e to a negative thing gets super tiny as n gets huge. And so what we'll say then is that goes to 0 as long as s is bigger than 1. Notice when s is bigger than 1, that's exactly when this is negative. So that goes to 0, and what are you left with? Well, you're still left with minus this fraction. Take that minus sign and distribute it down here to switch those around, so you get 1 over s minus 1. So we just did our first Laplace transform. The Laplace transform of e to the t is 1 over s minus 1, as long as we say that s is larger than 1. In other words, that'll be the domain of this new function. Depending on what kind of class you're taking, this is more important in like maybe a more advanced theory-based differential equations class, but if you're in a more computational one, then that information about the domain is not as important. So the Laplace transform is linear, just like the derivative was and just like integrals are. And what do I mean by that? I mean that if you're going to take the Laplace transform of some constant times a function f plus some other constant times a function g, remember that you can take constant multiples outside and you can split over a sum. That's what it means to be linear. So notice that I've split this into two pieces and I've pulled the constants out front. All right. If you weren't a big fan of doing this example up here, you're in luck, depending on what kind of class you're in again. It's pretty typical that in a textbook for differential equations, they just give you this gigantic table that says, hey, here's a Laplace transform for some pretty common functions that we'll run into. So a lot of the work comes from or maybe a lot of how we'll do Laplace transforms, is just trying to make our formulas fit these tables here. So how should you read this? So like the Laplace transform of e to the at is just the fraction 1 over s minus a, and in pink I've included the domain of each of these. And again, some classes don't worry too much about that than others. But what have I got here? I've got sine of at, it should be a over s squared plus a squared. I'm telling you that that's what that integral will spit out, so I'm trying to save you that amount of work. If you've never seen sine h before or cosine h before, or maybe a better way to say that is, some people say sinh and cosh, those are the hyperbolic trig functions. You don't really need to know anything about them other than their Laplace transform is this and this. And so to give you an example of how these tables work, let's maybe do a few. Let's try to compute the Laplace transform of t cubed s. So if I didn't want to use that integral stuff above, what I'd realize is, hey, that's not got the form t to the n. Its Laplace transform should be n factorial over s to the n plus 1. So n looks like it's 3. So it should be 3 factorial over s to the 3 plus 1. Final answer should be 6 over s to the 4th. Pretty cool. Let's do another one. Let's try to do the Laplace transform of sine of 2t times s. Well, I've got a formula for what the Laplace transform of sine of at should be. Looks like a is 2. Let's plug that in. You get 2 over s squared plus 2 squared. So that's me plugging 2n for a into that formula there. And if you simplify a little bit, you get 2 over s squared plus 4. So that is the Laplace transform of sine of 2t. Let's do one more. Let's do the Laplace transform of 2 cosine of t plus 3 e to the minus 5t. So here's where we're going to use our linearity property of the Laplace transform. I'm going to split that into the Laplace transform of 2 cosine of t, and then what I'll do is I'll pull that 2 out front, so that's this right here, plus the Laplace transform of 3 e to the minus 5t, and then what I'll do is I'll pull that 3 out front of that. So split that into its 2 pieces. Why should you do that? Well, because this has a formula. It's in your table, the Laplace transform of cosine of t. And then similarly, the Laplace transform of e to the minus 5t, that'll fit this formula up here. So we're using that linearity property to make use of this good table here. So the whole point of this then, you would get, this would be s over s squared plus 1. So for this cosine example, a is 1, so I'm plugging that in here. You've just got the 2 out front. And the exponential one, looks like the Laplace transform of e to the minus 5t should be this, so 1 over s minus negative 5. Just simplify some of those and you get 2s over s squared plus 1 plus 3 divided by s plus 5.